Hello and welcome to section 4.6 on graph sketching with calculus. In this section, we bring together the techniques of section 4.2, 4.3, 4.4, and 4.5 to sketch the graph of a function.
When we set out to sketch a graph of a function, there is a short list of topics which should be accurately depicted in the sketch. The domain of the function, intervals on which f is increasing or decreasing, concave up or concave down, local maximum and minimum points, inflection points, and any horizontal and vertical asymptotes. Let's take an example. We'll begin by sketching the graph of the polynomial f of x. Remember that a polynomial is defined on all real numbers, and to find intervals on which the function is increasing or decreasing, we begin by taking the first derivative. We factor a 3, and we factor the binomial. From the simplified first derivative, we are quickly able to identify critical numbers, those points for which the derivative is 0 or does not exist. A polynomial is differentiable at all points, so x equals 5 and x equals -1 are the only critical numbers of f. We divide the number line into intervals using the critical numbers, and we use the test points 6, 0, and -2 to determine if the derivative is positive or negative on these intervals. Using the increasing-decreasing test, we find that f is increasing from -infinity to -1 and 5 to infinity, while f is decreasing from -1 to 5. And using the first derivative test, as f prime goes from positive to negative at -1, -1 f of -1 is a local maximum point. And as f prime goes from negative to positive at 5, 5 f of 5 is a local minimum point for f. We use the unsimplified form of f prime to find the second derivative, which we simplify by factoring out 6. We divide the number line into intervals using the 0 of the second derivative, x equals 2. And we use the test points 3 and 0 to determine if the second derivative is positive or negative on these intervals. Using the concavity test, f is concave up from 2 to infinity, while f is concave down from -infinity to 2. The only inflection point for f is 2 f of 2. Calculating f of -1, f of 5, and f of 2, the y values for all local maximum, minimum, and inflection points, we are in a position to sketch all but the end behavior of the function.
In section 2.5,
and from your high school algebra class, the end behavior of a polynomial is dictated by the degree of the polynomial and the sign of the leading coefficient. Since the degree of the polynomial is 3 and the leading coefficient is positive, as x approaches infinity, f of x approaches infinity, and as x approaches -infinity, f of x also approaches -infinity. Before we sketch the function, let's summarize our information so we know how the graph should appear on certain intervals. We have 2 critical numbers and 1 inflection point, so we divide the number line into 4 intervals. On the first and the last interval, f is increasing, and on the middle 2 intervals, f is decreasing. While on the first 2 intervals, the function is concave down, and on the last 2 intervals, the function is concave up. Before we sketch the function, we now know roughly how each interval should appear. We complete our sketch by graphing the local extreme points and the inflection point. We note the function's end behavior. As x approaches -infinity, y approaches -infinity, and as x approaches positive infinity, y approaches positive infinity. And we now have our sketch. We've depicted all of the topics we're interested in. We know where the function is increasing and decreasing, concave up, concave down. We know where the local extreme points are, and we know where the inflection points are, and the end behavior.
you've seen the basics. Now gain mastery through practice and study.